Hi there. In this video, we'll look at the subject of modeling and optimization, a classic application of calculus that involves the use of derivatives. So basically the word optimization implies that we want the best conditions. Okay, we want to maximize some quantity or minimize some quantity. Okay, and of course modeling involves translating a scenario into a math problem, solving the math problem, and then translating the solution back in terms of the original scenario. Okay, so for this video I've selected problem 10 from the homework set on page 226. Really strongly encourage you to look at that problem and try your best at it for 10 or 15 minutes before watching the video, but just watch this video to help you learn the process if you're absent, or to help you if you get stuck, or to confirm that your solution is correct and that your reasoning was correct. Alright, so with that, let's go ahead and get started. If you look at the box at the start of this lesson in your textbook, on page 219, there's this purple box that says Strategy for Solving Max-Min Problems, and it's worth reading the material there. So I'm just going to read from that. Number 1 says, understand the problem, read it carefully, identify the information you need to solve it. Okay, so clearly, if we're going to make any progress, we need to do a careful reading, probably 2 or 3 times. Most of the time when you do a complex problem, it requires multiple readings. And so let's just read carefully and try to understand what it is that we need to do. So we're dealing with a p-patch here that's got area 216 square meters, okay, which is then going to be enclosed by a fence. And we then want to divide the p-patch into 2 equal parts, and some other fence is going to do the dividing, which will run parallel to one of the sides. Okay, and let me just try to make sense of what I'm reading so far before I continue reading this problem. Alright, so I'm just going to draw this p-patch, and I'm told that the area is 216 square meters. So altogether, this right here would be 216 square meters. Okay, so let me just make a little note of that. The area of the p-patch is 216 square meters. Okay, and it's arranged in a rectangular fashion. Okay, we then want to enclose a fence, so the purple line is a fence, and we want to divide it into 2 equal parts. So I can imagine doing that in a couple ways. This would divide into 2 equal parts. This would divide into 2 equal parts. This would divide into 2 equal parts. But we've got the further understanding that the dividing fence is running parallel to one of the original sides. So I could choose this one as a representation, or I could choose this one. Okay, and just out of curiosity, I wonder if it matters. Okay, if student A draws it this way, student B draws it that way, will the 2 students get the same answer? Okay, so I'll leave that as a challenge for you. All right, so with that, let's keep reading and see what it is that we're expected to do. What dimensions for that outer rectangle will require the smallest minimum total length of fence? Okay, and in particular, how much fence will be needed? All right, so I can see that this is indeed an optimization situation when we want the optimal length of the fence. Okay, if I'm paying for that fence, I'd like to pay as little as possible. I've got this p-patch that needs fencing. It's got a particular area, and I just want to minimize the amount of fence required to enclose it. Okay, so with that, let's start to now get a feel for what's going on. Okay, step 2, after we've understood the problem, and I do feel I understand what I'm expected to do. Step 2, develop a mathematical model of the problem. Draw pictures, label parts that are important, introduce variables, okay, and then write a function to represent the situation. So let's see what we come up with along those lines. Okay, so I don't know how wide and how tall this thing is supposed to be yet. So let's just use a variable to represent the height of our rectangle. And let's use some other symbol about y to represent the width of the individual components. Okay, you could just as well have chosen to call the entire width y, but that is up to you. You're in charge of symbols here. Okay, so I've chosen to use the symbol y just to represent that much distance right there. Okay, and so let's see what we can learn through careful reading the problem. What can we learn about the relationship between these variables? Let me just kind of move that to the side for a second. And why don't we clean up our area here before we continue. Just trying to avoid any distractions here as I work through this problem. Okay, so let's see. We are given that the area of the entire figure is 216. And knowing that it's divided into two equal parts, can I just divide that by 2? Half of 216 is 108. All right, so in particular, each one of the regions has area 108, making a note. All right, that's true for each region. And then the total area would be 216. Okay, so why don't I just write down an equation for this much. The length times the width will be equal to 108. And that describes each of these little sub-rectangles. Okay, so I'll call that relation number 1. I used the information in the problem about the area to come up with a relationship between the dimensions of the rectangle. All right, let me continue with that. What else can I learn here? Well, I'd like to be able to describe the amount of fence that's needed. So let's count. We've got x plus y plus another y plus x plus y plus another y plus this x that runs down the center. Okay. Now altogether, I counted 3 sides of length x and 4 sides of length y. So the amount of fence required is 3 times x plus 4 times y. Okay. And the result is some amount of fence. Why don't we use p as in perimeter? Okay. And this is now a function of 2 variables, which represent the length and width of the rectangles. Okay. And our goal now is to minimize p, least amount of fence. Okay, well, I'm not so good with 2 variable problems. This is a single variable calculus class. So why don't we try to somehow combine the information in these 2 equations so that it becomes a 1 variable problem. All right, and you really do have 2 choices. You could, maybe you don't really. Maybe your only choice is just to work with this equation. So let me just solve for y. I could just as easily solve for x. But let me write y in terms of x by dividing both sides by x. Okay. So let me just go through, and wherever I see y, I can replace that symbol with the expression 108 divided by x. Okay, so step 3, I'll rewrite this formula as a formula about the variable x. We'll take y out, and in its place, we'll write 108 divided by x. Okay, and now we have that the perimeter is a function of just the variable x. Much better. All right, so with that, this is where calculus now comes into play. We would like to arrange for the smallest perimeter. So this is just a minimum problem now. And so step 4, let's compute the critical points and endpoints and see what we can learn from that. Let me actually back up a step because I'm realizing I need to understand any constraints that may be involved in this problem. In other words, can x be a million? Can it be negative? Can it be 1/1,000,000th? What can it be? So as I look at this, and as I visualize some extreme cases, I can picture a very short and wide rectangle like that that would have the correct area. Okay, and as I think about this, it occurs to me that the minimum value of x, the height, should be some positive value. Okay, so we can make it very, very short. If we actually made it 0, it would have no area, and that doesn't fit the conditions of the problem. So we need x to be a positive number, for starters. Okay, now, can x be as large as you want? In other words, can you have a very, very tall p-patch like this? Well, let's think together. Okay, if this is like 100,000 meters tall, I feel like if I make it just short enough, okay, if I make the width short enough, I should be able to arrange for the area to be what I need it to be. In particular, did I do that correctly? No. Let me try this again. In particular, if I take 216 and divide it by that large number, now that I've done it correctly, when I multiply the length by the width, it will indeed produce the correct area of 216. So it feels as though there's no upper limit here for x. We need x to be positive, can't be 0. But other than that, there are no constraints on the problem. So I'm going to go forward with that understanding, and I'll just go ahead and clean this up to make room for what's coming next. Okay, so now I know what constraints I'm dealing with. Not many constraints. All right, and I will adjust my technique accordingly, knowing that there's no upper bound here. All right, if we were dealing with some closed bounded interval, for example, then we could use certain techniques. But with these open unbounded intervals, we'll need these other techniques. So let's get going on this. Okay, so time to go ahead and start taking the derivative. Recall that the whole chapter is about applications of derivatives. What can you do with derivatives? Well, you can solve this p-patch problem for one. So the derivative of 3x is 3, and the derivative of 4 times 108 over x is going to require a little bit of work. So let's just do a little side work on that expression. Okay, can I just multiply these together? 4 times 100 and 4 times 8 is 432. All right, and if I just think of this as a power, okay, that will help me now to apply the power rule. Okay, so we're going to get 432 times negative 1, drop the power 1, and we get this expression. Okay, so this is an expression for the derivative. And to find critical numbers, we'll ask, where is that undefined, and is it ever 0? Okay, so let me just rewrite the formula in a more familiar form. Can I use a minus sign here? I guess I can. Okay, so this is an expression for the derivative of p. Great. All right, is this ever undefined? Well, can't divide by 0. So if we try to write 0 for x, we get that the derivative is undefined. But already knew that. X can't be 0 from our constraints discussion, so that doesn't really add anything. However, I should be concerned about whether p prime is ever 0. So p prime is 0 sometimes, potentially, when these two values are equal, since then they will subtract to equal 0. Okay, so now we have a little problem of algebra. Are these two expressions ever equal? Let's find out. Multiply by x squared And let's divide both sides by 3. Let's see here. 1, 4, 3. Did I do that correctly? Okay, and then we just take square roots. And ordinarily we'd want the positive square root and the negative square root, but we know x can't be negative, so we'll just ignore that. And we'll say that's our answer. Okay, so this is one of the critical numbers, in fact the only critical number of this function. Well, I guess there are 2 critical numbers, it's just that we're ignoring one. Alright, so there's one relevant critical number. And so now it's time to wheel out the first derivative test. Okay, we can't just say, oh, plug in the endpoints, plug in the critical points, and be done, because we don't have any upper endpoint to deal with. All right, so we need to use the first derivative test for local extrema to know whether at this particular value we get a min, a max, or a shelf point. Okay, so let's figure out what's going on. Okay, so let me list the critical number, an x value that's important, and let me go back to my formula for the derivative, okay, which is here. And what we need to do now is we need to figure out what happens when we plug in values that are greater than that critical number or less. We already know, and let me just shrink this down so I can operate with this shrinking. There we go. And we'll pull that down to where I can see it. Okay. So we already know what's going to happen when I plug in the critical value. If we've done our math correctly, we should get 0. So the question is, if you plug in something larger, like 1,000,000, what's going to happen? Okay, so we're analyzing this expression when x is 1,000,000. We're getting 432 divided by an awfully big number. Okay, and that feels like it's going to be less than 3, so 3 minus something small should be positive, we would expect. On the other hand, if you use something that's less than this critical number, but still positive, how about 1, for example, you're going to get 3 minus 432 over 1 squared, which you can tell is a negative value. Okay, so I'll just write 0 in there between, so we know that the derivative is undefined. I'll put UND, undefined. And so if x is higher than 0 but lower than this critical number, its derivative is negative. If x is higher than the critical number, the derivative is positive. And what does the first derivative test tell us? Well, it says if the slope is negative, the function is decreasing. If the slope is positive, the function is increasing. And at a point where the derivative changes from negative to positive, we should expect a local min. Okay? And let's see what else we can learn from this. Okay? So within the range of values for this, for which the function is defined, okay, which starts at 0, the information about the derivative is telling us that the function is decreasing up to that critical value all the time. So that tells us that there's no value over here that's lower. And furthermore, the information about the derivative tells us that forever after, all the way up to infinity, the function is going to be increasing. All right, so what that tells us is not only is this a local minimum, it's actually the global minimum of the function, and that's what we were seeking. All right, now it's been so long since we talked about this fence problem. Let's get back to it and try to kind of pull things together. All right, so let me go over here and just pop this problem down, and let's try to wrap it up. Here goes. So on the previous screen, we got that x should be the square root of 143. And so that's the height of the optimal rectangle that will allow us to enclose our p-patch and divide it down the center and so forth in such a way that uses the least amount of fence so that we can save money at the hardware store. Okay, and so now it remains to find the other dimension. So we want dimensions, length and width, for the outer rectangle. And we've got the height. It remains to find the width. Well, can I go back a stage for a second? We determined that the area of each little small rectangle is 108. So we need this to be 108 and this to be 108. So we need y to satisfy the equation y times the height equals 108. And so we can just use division here. And at this point, perhaps it makes sense to wheel out a calculator and approximate these values. So the square root of 143 is about 11.96. If you round, it's about 11.96. And the value of y, which is 108 divided by that value, is about 9.03. If we take two of those y's together, we get 18.06 approximately. Okay, so if our math is right, then this is indeed the dimensions of the outer rectangle that require the smallest total length of fence. And last component, how much fence will actually be needed? Well, let's figure out. Okay, so we've got this vertical part, and then the one down the center is going to be needed, and then this one. Okay, and I think what we can do at this point is use our previous work in terms of the perimeter function. We got that the total amount of fence that's required is 3x's plus 4y's. So let's just go ahead and record that right here. The perimeter is 3x's plus 4y's. Okay, so if we go ahead and compute, you can just throw this in a calculator at this point. We got this value for x and this value for y. Okay, so let me just throw that in. 3 times this square root plus 4 times this ratio of 108 to the square root of 143. Okay, and I'm getting that this is like 72. Is that surprising that the answer is a whole number? The amount of fencing, so can I just write this out? We need 72 meters of fencing to enclose the pea patch, which has area 216 square meters, and which we've enclosed with a rectangle and divided into two equal parts in such a way that the fence down the middle is parallel to one of the sides. Alright, so we've solved the fence problem. Our pea patch is now properly fenced in. Okay, presumably we'd like to keep those rabbits out. Alright, so hopefully that will help with that. I hope this video is helping you to understand how to use modeling to solve problems. And let's go a step further with this. I'm going to fire up Desmos right here. And let's see if there's something to learn by examining the graph of things. Okay, so let me go back to my model from the previous screen, in which we were able to express the perimeter as a function of the height of the region. So 3x plus 4 times 108 divided by x. Let me get that typed in. Let's call P of x equals 3x plus, can I see it again? 4 times 108 over x. 4 times 108 over x. Okay. And can we see the graph of that? The graph looks hidden. What's the deal? Well, maybe we need to zoom out somewhat to see it. No, it doesn't seem to be helping. Oh, there it is. Okay, just needed to zoom. Okay, so let me see if I can fix up my x parameters here. We'll go negative 50 to 50. All right, now I can actually see more of the graph. Better use of my screen. Okay, right here, can I drag on this curve somehow? All right, we see that there's a minimum at 1272. Is that really the min? And a maximum point at negative 12, negative 72. Okay, and this looks like an odd graph, so we could think about why it was odd, but notice everything down here in this area, over here, involves impossible dimensions of the rectangle. So we might as well just ignore all of that. Okay, why don't we even go back and make this official and type x is greater than 0. Okay, now we have that constraint, and we see the minimum value. When x is 12, the value is 72. Now maybe I should have bothered to compute the square root here. I don't think that's a perfect square, but this makes me want to sort of re-examine my work because I'm surprised that both of these values are whole numbers. So 72, I think, came up in the analysis. In fact, it did. We need 72 meters of fencing. But let me just wheel out my calculator one more time and see what is the square root of 143. I'm getting 11.95 as opposed to 12. Maybe Desmos is just rounding here. Maybe that's what's happening. So can I get more specificity on that, Desmos? I'm not sure how to make that happen. Okay, so maybe this isn't in fact the whole number. Our answer looks suspiciously like a whole number for the total amount of fencing, whereas the height wasn't a whole number. It was the square root of 143. And it occurs to me square root of 143 is awfully close to square root of 144, which is exactly 12. So this is pretty darn close to 12. All right, in any case, just wanted to bring that graphing perspective to bear. Getting back to that purple box on page 219, it says number 3, make a graph of the function, find the domain, determine what values make sense in the problem. We did that along the way. The graph that we see is actually supporting our conclusion in terms of seeing a minimum. And what else? Step 4, identify critical points and endpoints. We did that. Solve the model. We did it. Interpret the solution. And we've done that. Okay, so once again, I hope that this video is helping you to develop your skills in regards to modeling and optimization. We'll see you next time.